Our next
Great.
speaker is Joaquin Liniado. He's a PhD student at the Instituto de Física de La Plata. He will be talking about gauge theory and integrability. Thank you, Joaquin.
Bueno, thank you very much. Thank you very much to the organizers for giving me the possibility to speak in this conference. I will talk actually about higher gauge theory and integrability, and this is based in some work I did a couple of months ago with Han Chen. Okay, so given that this is a conference on holography and not on integrability, I thought it would be a good idea to start with a drawing, which I stole from my friend Lewis Cole. So this is a landscape of differential equations. In the bottom left corner, we have linear differential equations, which are represented by a very nice garden with a nice lake and some mountains and some flowers, because we usually know how to solve linear equations. And whenever we have a system which is described by linear equations, we're very happy. But as we go out of this little garden, we find ourselves in this arid desert of nonlinear equations, which is the kind of equations which usually appear in physical systems. And of course, there are techniques to solving nonlinear differential equations. There is a particularly important one, which is perturbation theory, which somehow approximates the problem of solving a nonlinear differential equation by kind of a linearization procedure. But of course, perturbation theory doesn't always work. Perhaps the most important example is strongly coupled QCD, the low energy limit of QCD. But also in this arid desert, there are some oases, which are represented here by these little lakes in the middle of the desert, which are integrable equations, which are also nonlinear differential equations, but for some very special reason, they are solvable. So integral systems are usually characterized by having a large number of symmetries. A large number of symmetries gives a large number of conserved quantities via another theorem. And it is precisely this large number of conserved quantities which eventually may lead to the exact solvability of the problem. Now, the problem about integrable systems is that given a theory, given a system, it is very difficult to know a priori if this system is integrable. So to address this question, at least in the case of systems in 2 dimensions, in the 1960s, Peter Lax came up with a criteria. So he said, let's say we have some field theory on a 2-dimensional manifold sigma, and we look for what's known, you have to look for a Lax connection. So a Lax connection is a connection over some bundle over this manifold sigma, which is constructed in terms of the fields of the theory. And his criteria says, okay, if the equations of motion of your theory are equivalent to a flatness equation for this Lax connection, then your theory is integrable. So why this is the case? The reason why is because having a flat connection allows you to construct the conserved quantities, and this is done using holonomies or Wilson lines. So let me briefly remind you what a holonomy is. So say you have a path, gamma, on sigma. One can define its holonomy as the path order exponential of the connection over this path. In particular, the holonomy or the Wilson line is a solution to a parallel transport equation along the curve. A crucial thing about holonomies is that if the connection is flat, then the holonomy, this path order exponential, is independent of the choice of path as long as the paths have the same endpoints. In other words, if you have 2 paths, gamma 1 and gamma 2, which are homotopic relative base point, meaning you can deform one into the other, holding the endpoints fixed, then the holonomies of this along these 2 paths coincide. The fact that one have this independence of paths is precisely what allows you for the construction of the conserved charges, and this is what lies behind the integrable structure of the model. Now, the problem is that Lux came up with this very nice idea of constructing a connection, which is on-shell flat, but he didn't say how to construct this connection. He only said, if you are able to construct this connection, then you will be able to construct the integrable structure, but he didn't say how to do it. And it took almost 60 years for someone to come up with an idea to do so, and this was a series of papers by Costello, Witten, and Yamazaki. So they said, okay, where do we find connections in physics? And well, we all know that connections appear in gauge theories. And there is a very special example of a gauge theory, which is Chern-Simons theory, which is a gauge theory defined over a three-dimensional manifold. This is the Chern-Simons theory form. And the equations of motion of this theory are precisely a flatness equation for this gauge field. Now, Chern-Simons theory has been known for 50 years, and still it took 50 years for people to realize how to actually use this to construct a two-dimensional integral theory. And the crucial idea that Costello, Witten, and Yamazaki present in this paper is to introduce what's known as disorder defects. So very schematically, what they do is they start with Chern-Simons theory on this three-dimensional manifold. They take this real line and then they complexify it and compactify it to the Riemann sphere. And they define this four-dimensional holomorphic Chern-Simons theory, which is basically almost the same as Chern-Simons theory. But now X, which is this guy here, has 4 dimensions. This is a 3 form, so now one has to introduce a 1 form here. And this 1 form is a meromorphic 1 form, meromorphic because it has poles along the holomorphic direction of the CP1. And this is the crucial object that they introduce, because these poles that this 1 form has actually act as a boundary of this 4-dimensional manifold. And the idea is that whenever you have a gauge theory defined on a manifold and you put a boundary on this manifold, the boundary breaks, at least partially, the gauge symmetry of the theory. And whenever you break gauge symmetry, the process of breaking gauge symmetry induces dynamics wherever that symmetry was broken. So schematically, the idea is that they start with this 4-dimensional theory over this 4-dimensional manifold. They have these poles over here, and these poles break the gauge symmetry. The breaking of the gauge symmetry induces dynamics on these two-dimensional manifolds. And crucially, given that the equations of motion of the parent 4-dimensional theory, which was this holomorphic Chern-Simons theory, were flatness, these dynamics are inherited by these two-dimensional, by the two-dimensional degrees of freedom. And so one finds a way to construct two-dimensional theories whose equations of motion are by construction equivalent to the flatness of a connection, which, as I said before, was what allowed you to construct the integrable structure. So the main takeaway of 4D Chern-Simons theory is that it's basically a machine of constructing two-dimensional integral field theories in a systematic manner. So, well, with the idea that we had with Hank was to try and generalize this to 1 dimension higher. And as I said, the construction of the conserved charges in 2 dimensions was based on these holonomies, or these Wilson lines, which are basically integrals over paths. And so our idea is that the construction of the conserved quantities in 3 dimensions will be based on integrals over surfaces. So we will work with a 3-dimensional spacetime that I will call Y, and say we have some principal G bundle over Y with some connection. And the idea is that we want to construct a surface holonomy, and we will do this using the line holonomy, so the Wilson line of this connection that we have on this bundle. Now, the trick to doing this is to define surfaces in a very special way, and we will define surfaces working with paths on path space. So what do I mean with this? Path space is the space of all paths. So this is path space, and a path on path space is a surface. Why? Because, say, we have this big gamma, which is a path on path space. Gamma defines a surface since gamma of naught is a path, gamma naught. Gamma of 1 is another path, gamma 1. And for every t in between, you have all of these paths, which altogether form a surface. So the idea is that we say, okay, one construct holonomies as path order exponentials of connections. Well, we will define a connection on path space, and we will consider the holonomy of this connection on path space. But crucially, now this path on path space will be a surface, so actually, secretly, this holonomy will be a surface order exponential. So people have done this a long time ago. People have constructed connections on path space, and you can do this by introducing a two-form, which I call B, and this connection on path space is defined in terms of this two-form B, and W, which W is the Wilson line. So secretly, this new connection A on path space depends both on this two-form B and on the connection over the original bundle through its Wilson line. So once we have this connection, we can define what I will call a two-holonomy, which is the path order exponential of this new connection over gamma, which in practice is a surface order exponential over the surface defined by gamma, which I call sigma, of the inverse adjoint action on this two-form. So remember that in the two-dimensional case, the construction of conserved charges depended on the independence of the holonomy between homotopic paths, and the fact that the holonomy was independent of the path was related to the flatness of the connection. So in this case, the idea is that we will the idea is that if this connection is flat, then this holonomy will be independent of the surface. Now, crucially, the flatness of this connection implies two equations which relate A, which is the original connection, and this two-form B. In particular, if one can construct a connection, if this connection cal A such that is flat, then this will allow us to construct conserved quantities. So we once again find the same problem, which is how do we actually construct a theory whose equations of motion imply these higher flatness conditions. So this brings us to what's known as a categorical ladder equals dimensional ladder proposal, which is a proposal that came up a couple of years ago, that says something like that you can describe higher dimensional systems by going up in the categorical ladder. So let me briefly say what this means. So Chern-Simons theory is a three-dimensional theory, which is described using two main structures, which is two main mathematical structures, which is a Lie algebra and a Lie group. And Lie algebras and Lie groups belong to what's known as categories, and one can define a generalization of a category, which is called a two-category. And so one replaces one Lie algebras by two Lie algebras, and this proposal says that if you are using two Lie algebras, then this will describe a four-dimensional system, and one can go higher and consider three Lie algebras to describe five-dimensional systems, and so on and so forth. Okay, so this is what we did. The idea is that we will work with these two Lie algebras. So let me say what these are. Basically, a Lie2 group or a two Lie group consists of two Lie groups, H and G, and some map mu1 between these two groups. And correspondingly, a Lie2 algebra consists of two Lie algebras, which is the algebra of H, the algebra of G, and this map which integrates to the map between the groups. And in particular, this Lie2 algebra has three different brackets: the bracket in G, the bracket in H, and some bracket which mixes H with G. And as usual, we can equip our two Lie algebra with a bilinear form, which in the usual case is the trace, that we can use to write down our actions. So this is something people have been doing, higher gauge theory, which is basically defining a gauge theory using these higher structures. And the field content of a two gauge theory is called a two connection, which is a generalization of a connection, which actually consists of two objects, A and B. So A is a G-valued 1 form, and B is an H-valued 2 form. So we see that this object here looks very similar to the things we were looking at before when we were talking about surface holonomies. For completeness, in higher gauge theory, one can also consider higher gauge transformations, which are given by, as usual, a smooth valued function, but now also one adds this H-valued 1 form, and these gauge transformations act in the connection, in the usual connection, in the usual way, plus this additional term, and well, in the usual gauge theory, one doesn't have these two forms, so it doesn't matter. Okay, so in the same way that one can define a curvature for a usual connection, which is the usual expression for a curvature, one can define a curvature for this two connection. And the curvature has this form, which has two parts, which I will call them separately. So the first part I will call the fake curvature, because it's very similar to a curvature, but it is corrected by a B term. And then the two curvature, which is this basically covariant derivative of B. So as a reminder, the equations this equals to 0 and this equals to 0 were precisely the equations required for the two holonomy to be independent of the choice of surface. And if we are able to construct a two holonomy which is independent of the choice of surface, then this will allow us to construct conserved quantities. Okay, so the last step is to introduce homotopy Morgan theories, which are basically action functionals whose equations of motion are given by flatness of whatever connection you are talking about. So for a Lie algebra, the homotopy Morgan theory is Chern-Simons theory, whose equations of motion are flatness of the one connection. For a Lie II algebra, one can define a higher version of Chern-Simons theory, which we call two Chern-Simons theory, which is basically an action functional whose equations of motion are the flatness of the two connection, which, as I said before, are these two equations here. Now, one thing to note is that F is a 2 form, B is a 2 form, so this is a 4 form. So we can see that this is actually an action over a 4-dimensional manifold, and this is where we see the manifestation of the categorical ladder equals dimensional ladder proposal.
Joaquin, you have 3 more minutes.
Okay, thanks. So what did we do? So Costello and Yamazaki started with 3D Chern-Simons theory. They went to 4 dimensions to then construct 2-dimensional integral field theories. So what we did, we said, okay, let us categorify this story. So we will start with 2 Chern-Simons theory. We will complexify and compactify to go to 5D, and then study the boundary theory to obtain a 3-dimensional integral field theory. So basically, this is what we did. We start with this 4-dimensional manifold. We complexify and compactify to CP1. We introduce this guy here that has poles. The poles partially break the gauge symmetry of the theory. Breaking the gauge symmetry induces dynamics on the boundary. And so we find schematically a very similar story to the one we found before. Now, Y is a 3-dimensional manifold. I didn't want to draw a cube to make it neater, but this is now a 3-dimensional manifold. And the idea is that we induce a theory on Y whose equations of motion are, by construction, these two flatness equations, which, on the other hand, are related to the integrable structure because it is what allows us to construct the conserved charges in 3 dimensions. So the main takeaway is that this holomorphic variant of 2 Chern-Simons theory we introduced with Hank actually allows you to construct 3-dimensional integral field theories in a systematic manner. And to conclude and close, we have actually managed to extend Costello's and Yamazaki's framework to systematically construct 3D integral field theories. One thing I didn't say is that, well, this choice of this meromorphic 1 form with poles is a choice, and different choices lead to different theories. So there are still many choices to try and many 3D IFTs to construct. And then one could expect going higher in the categorical ladder to construct 3 Chern-Simons theory and then 4-dimensional IFTs and so on and so forth. thank you very much. There is a paper in any case. Someone wants to see it.
Thank you, Joaquin. Very nice talk.
Thank you very much.
So our first question by, I think, Miroslava.
Hi, Joaquin. Very nice talk. I have a very nice question.
Yes.
So, why do you require flat connections mathematically and physically speaking? What do you gain with a connection being flat?
So you need the connection to be flat so that the holonomies you construct, which are the Wilson lines, they don't care about the formations of your path. So when you construct this object here, which is the Wilson line, is an integral over a path, and if this connection is flat, then you can choose two paths, which, as long as they share the same endpoints, you can deform one into the other, and this object here will not care. It will give you the same value on one path or on the other. In particular, that's not true if the connection is not flat.
Okay. Okay. Thank you very much.
No problem.
Carlos, next question.
Okay, Joaquin, thanks very much. I liked a lot the talk because I was writing questions and you were answering them one by one, right? But let me ask you one thing. This message maybe you told me but never percolated in me. Is it correct to think that the trick to have a non-abelian B2 is that you can make it because you need of the one form, right? So this object you construct needs of the one form. Is the B2 alone cannot exist. Is that correct?
I don't know if what allows B to be non-abelian is the fact that you are also using the original connection, this A, to construct it. I would say it's a combination of you putting the A, but also adjusting the equations you get, which are these two. These two equations are the ones you get in order for this V to be independent of the surface. And I'm not sure if it's only because you have included A. I would say it's a combination of you including A, of you constructing this holonomy, not naively, but as using this construction of a bundle over path space, which is quite subtle. It's not something that certainly we didn't come up with that. That's something people have done before. So I wouldn't know the exact answer. I'm not sure if it's yes.
Let me put it differently, and very quick. I'll ask you two questions. One would be, suppose that I make B abelian. Can I have B2 alone? Looking at those two equations, with A abelian, I can have B alone. A and B both abelian. Right? I can have only B2, right? And I just need to be close.
In B2 is B, no?
B2 is B. Yes, sorry.
Yes.
Okay. And final for me, suppose that I give you a 3D gauge theory that I know is integrable, right? Could you find what's your lax connection?
So integrability in 3 dimensions is not something as standardized as in 2 dimensions. So if you talk with someone integrability, someone will say, okay, integrable, what's a lax? In 3 dimensions, it's not something that is standardized. It's not something that is kind of defined. And people have not worked a lot in 3-dimensional integral field theories. So actually, there isn't even a notion of a lax. So this is a proposal actually of a lax connection for a 3-dimensional setting. I think there are only literally 2 models that are studying 3D and that they are integrable and in different senses.
Thanks very much. Thanks very much.
Thank you for
okay, so we have time for one last question by Arpan Kundu.
Hi, first of all, thanks for nice talk. So I had a question like if you go to the like higher in the categorical ladder, so
Mhm.
if you, for example, have like 3 Lie algebra,
Mhm.
what are analogs of this bilinears?
So if you have a 3 Lie algebra that consists of 3 Lie algebras, and so you can have 3-gauge theory. So a 3-gauge theory will have the connection on a 3-gauge theory will have A, B, and C. So behind this, I have not gone into detail, but there are like L infinity algebras, and so there is some grading involved in here. But you would have 3 objects, which will be a 1 form, a 2 form, and a 3 form, and you would be able to define 3-gauge transformations, which will be given by as function, a 1 form, and a 2 form, and then you will be able to construct a homotopy Cartan action, which will be a 5-dimensional action, which will depend on A, B, and C, and whose equations of motion will be some 3 curvature, which will also have 3 terms and 3. I'm not sure if this answers your question.
Yeah, I think.
Okay.
Okay,
Thanks.
so we thank Joaquin again.
Well, thank you very much.